Okay, so this time the agenda is formal charge and bond order. So we're going to look into the mathematics in terms of working this thing out, formal charge. Okay, so first of all, be aware that for the nitrate group, what you're talking about is actually the conjugate base of the acid, nitric acid, HNO3. So this electron that we're talking about here, this negative, doesn't just come from nowhere. It actually comes out from the dissociation of HNO3, in which the electron is donated to the NO3 group, and that's how you end up with that negative. And the negative is an electron. That's the key thing there. Okay, and from our electronegativity table, you can see here's nitrogen and here's oxygen. Nitrogen's got an electronegativity of 3.0 and oxygen is 3.4. So for that reason, you're going to see the least electronegative at the center of this molecule. So in the skeleton that I've drawn of the NO3, that's exactly what you see. I've circled the nitrogen here, and you see that it's the least electronegative of the two of them. Also notice that here we have group 1, group 2, and if we skip across the orange line there, we have group 3, 4, and nitrogen is in group 5, oxygen is in group 6. So therefore, over here we've got nitrogen with 5 valence electrons from group 5, and for the oxygen we've got 3 times 6, oxygen being in group 6, so 3 sixes gives 18, and we've got the negative, the electron that was donated from the hydrogen ion. So altogether, for all of the bonds that are going to take place between the nitrogen and the oxygens, we've got 24 valence electrons that have to be satisfied in terms of the octet rule, which means they've got to have 8 electrons on their outer most energy level. Now for the initial bonds in the skeleton diagram, we've worked from the inside out. So in other words, we've used the valence electrons associated with nitrogen. Now here's the funny thing, nitrogen has got a valency of 5. Each bond takes 2 electrons, which means 2, 4 and 6, but we've only got 5. So the extra electron is coming from this electron that's been donated from the hydrogen from the acid. Next, you see in this diagram we've augmented the skeleton diagram, and what we've done is we've taken the 18 valence electrons from the oxygens and we've just encircled the oxygen with them. So we've got 1, 2, 3 lone pairs for each oxygen as it stands. Now there is a hiccup. At this point, the nitrogen does not have a fully satisfied octet, i.e. it's got 2 electrons, 2 electrons, 2 electrons from its bonding pairs. But it needs 8 electrons in order to be a complete octet. So what happens is that the oxygen over here has got a lone pair, and that lone pair is converted into a bond pair, which you see over here, and in that way then we have 1, 2, 3, 4 by 2, which is 8 electrons, and so nitrogen now has a full octet, as well as indeed all of the oxygens as well. They all have a complete octet as well. Next, what we've got to do is we have to work out the formal charges for each atom that's in the molecule. Okay, so over here on the left is the method for doing it. We've got 3 numbers for each atom, and basically the technique for that is outlined. Let's just have a look at that. Okay, so pay particular attention. It takes a lot of attention this, so full attention. What you're looking at, the numbers are, this number here is the valency of the oxygen atom. So this is the valency of the atom in question. 6 for oxygen, 5 for nitrogen, and 6 for oxygen again. Now the 1 is half the number of electrons in bonding. So the bonding electrons, you get half of that. So for instance here you've got 2 electrons that are involved in bonding in this bonding pair right here, and divided by 2 gives you 1. and then that's minus the number of electrons that are in the lone pairs. So those are the three figures. So in the lone pairs you've got 2, 4 and 6, and that's where your three numbers come from. Valence, half the number of bonding electrons, minus, now they're both minuses there, and then the number of lone pair electrons. Do a summation on that and you come up with your formal charge. In the end we've got +1, -1 and -1, which gives us an overall, well, these two cancel each other out. +1 and -1 cancel, and you're left with a -1, which is totally consistent with the group that we're talking about, HNO3 with 1 negative, and that's exactly what we've calculated. And finally, the bond order then is worked out by knowing the number of bonds. The number of bonds, which is 4, if we look over here, you've got 1, 2, 3, 4 bonds, divided by the number of resonances. Okay, and that's got to do with the fact that this double bond may exist here, here, or indeed here. Okay, so you've got 3 resonances, so the answer is 4/3 is what the bond order is. In conclusion, you've just got this important fact down here that no Lewis diagram is complete without formal charges. Lewis diagrams, to be complete, have to examine such mechanisms, and so it needs to know what atoms are electron deficient and which atoms are electron rich. As it says here, this is vital in analysis of the actual molecule.